Survey of Calculus, Chapter 1, Section 1, Limits, a numerical and graphical approach. Now, the idea of a limit is nothing new. You have it in life. You have maybe a spending limit when you go shopping, or there's speed limits on the road. So we understand the idea of limits. A spending limit, for example, is an amount of money that we can approach, possibly even reach, but cannot go beyond. Speed limit, same idea, although I think a lot of us probably go beyond it more than we should. A mathematical limit is very similar. It's a number that y approaches as x approaches a given value. So think of it this way. You have a graph in front of you, and with your pencil or your finger, you trace along the line or the curve toward a particular value of x. Now, as you're going along that curve towards that x value, there is a value of y that you are also approaching. As with limits in life, we may actually reach that y value, and that is called the limit, or we may not. It just depends on the graph, and we'll talk about that. So look at this given graph here. Just a nice simple graph of a line. I'm going to follow the line from the left, so go from the bottom left there to the top right. As your x values change and get closer and closer to 4, what do the y values get closer and closer to? Okay, well, if you look at the graph, they get closer and closer to 11. Now, what if you follow the line from the far right? So start at the top right part of the line and then go down, lower your x values towards 4. Do you approach the same y value? And the answer is yes, you approach 11. Can x actually equal 4? Is there actually a point at 4? Yes, there is. And what is y when x equals 4? Well, it's 11. Limits equaling 11 and the value equaling 11. Now let's look at the table. And again, at the top we're starting with low x values and working our way towards 4. And then the bottom we're starting with the higher values and working as we go up, working our way towards 4. So the x values are approaching 4. The input values are approaching 4. And what do you notice about the matching y values? Well, from the top, they increase, and the closer you get to where x equals 4, the closer the y values get toward 11. If you go do the same thing from the bottom, looking at the y values as x approaches 4, again, you see them getting closer and closer to 11. And what all this means is that the limit of the function f of x equals 2x plus 3 as x approaches 4 is 11. Okay, so we have a definition here. As x approaches a, the limit of f of x is L, and we write it like you see here. Limit, Lim for limit, and then at the bottom you have x, an arrow, and a number. That means as x approaches a, as x approaches whatever number, then f of x is the name of the function equals L, and L will be the value of the limit. If all values of f of x are close to L for values of x that are sufficiently close, but not equal to a. In other words, x doesn't actually ever have to reach a. It can approach it but not reach it. It could reach it, but it doesn't have to. The limit L must be a unique real number. So we're dealing with real numbers here, and there has to be a definite value that we're approaching. For example, a moment ago, this is what we were looking at if we want to write it out using this terminology. It's the limit as x approaches 4 of 2x plus 3, and that equals 11. Now, as we looked at the example, we looked at the graph from both the left and the right ends. In other words, we looked at the left hand and the right hand limits. We used the following notation to designate left and right hand limits. Okay, so if you look at this, look at the underneath the limit. You see x approaching, and then you have a number with a little plus, kind of like a power. And what that means is that we are going from the right. Think right is positive, so you're coming in towards the x value from the right of it. And that is the right-hand limit. If you have a little minus there instead, that indicates the left-hand limit. So that means you're starting to the left of the x value and coming towards it. In order for a limit to be said to exist, then both the left and the right-hand limits must be the same. In other words, the graph has to be heading toward the same y value from both directions, like it was in our example. Theorem, as x approaches a, the limit f of x is L if the limit from the left exists and the limit from the right exists and both limits are L. In other words, if the limit of f of x as x approaches a from the left is L and the limit of f of x as x approaches a from the right is L, then the limit as x approaches a of f of x is L. So in other words, like we said, you have to be heading toward the same y value from both directions. So let's do a little check here. Let f of x be x squared minus 9 over x minus 3. A couple of questions. What is f of 3? And what is the limit of f as x approaches 3? Pause the recording, give this a try, and resume to check your answer. Okay, first of all, if we put in 3 for x, we get 3 squared minus 9 over 3 minus 3. And when we simplify that, we get 0 over 0, which is undefined. So f of 3 does not exist. However, if we look at the graph, we notice that as we approach 3 from both the right and left side, we approach the same value, which is y equals 6. You can also see this using the table. If you go at 3 from the lower numbers and as you go from the higher numbers, what you're missing in there for your y value is 6. So the limit of f of x as x approaches 3 is 6, which notice that the limit exists even though the point itself doesn't. And that's why we said that x is approaching 3, but it doesn't ever actually have to get there. And that's the idea behind limits. It could get there, but it may not. And we could still find the limit even if it doesn't exist at that point, just like we found here. All right, let's try an example. Consider the function h given by, we have a little piecewise function here, 2x plus 2 if x is less than 1, and 2x minus 4 if x is greater than or equal to 1. We're going to graph the function, find each of the following limits if they exist, and when necessary, state that the limit does not exist. So we're going to find the limit as x goes to 1 and the limit as x goes to negative 3. It helps if you graph it first. If you want to do this in your calculator, remember that what you need to do is put in 2x plus 2 in parentheses, and then next to it, multiplied to it in parentheses, x less than 1, and then put a plus, and then 2x minus 4 in parentheses times x is greater than or equal to 1 in parentheses. If you've forgotten where the greater than, less than symbols are, you're going to hit second math, and that's where you're going to find all of those symbols. Pause the recording, give this a try, and resume to check your answer. At the graph, we have it graphed here, so make sure you graphed it correctly. We need to look at the graph as we approach x equals 1 from both the left and the right. And it's actually kind of easy to see when you look at it from the left as x approaches 1. It looks like y is heading to 4, and from the right it's heading to negative 2. Since we're not meeting up at the same place, the limit does not exist for x approaching 1. Now, look at it for x approaching negative 3. There's no break there. It's pretty much a continuous line. As you look at it going from both directions, you're heading toward the same number. So the limit as x approaches negative 3 of f of x is negative 4, and it does exist. All right, let's try another one. Calculate the following limits based on the graph. Pause the recording, give this a try, and resume to check your answer. So as we approach 2 from the left, we get 3. As we approach 2 from the right, we get 3. And because both of those are equal, the limit as x approaches 2 of f of x is 3. Now again, does the point 2, 3 actually exist on this graph? No, it doesn't. But that's not the question. The question is, what is the limit? What are we approaching as x approaches 2? There's another way we can do this. We can draw a wall, really just a line at x equals 1, and you'll see that in blue on the graphs that follow. We follow the curve from left to right until we hit the wall, and then mark the location within x, assuming we can figure out where it's hitting the wall. Then we follow from right to left and mark that within x, and if the x's are on top of each other, then we have a limit, and if not, the limit doesn't exist. Okay, so this is what it looks like. You've got your wall there drawn in blue, And as you approach x equals 1 from the left, you have an x there at y equals 4. As you approach from the right, you have an x there at y equals -2. So the limit does not exist because they don't end up in the same location. This one, on the other hand, as you approach from the left and from the right, both locations end at -4. So the limit does exist and it equals -4 when x approaches -3. Consider this function, graph it, and find each of the following limits if they exist, and if they don't, then say that they don't. Pause the recording, give this a try, resume to check your answer. Okay, so we have the function graph there, and I've put in a line or a wall, if you will, at where our limit is supposed to be, or where x is approaching. And so right here we have when x approaches 3. If we look at it from the left and from the right, it's pretty easy to see that they are meeting up at the same point. The table will confirm that. When x approaches 3, y is approaching 4, so the limit does exist and it equals 4. Now, looking at where it approaches 2, if you look at the left and the right, really what 2 is, it's a vertical asymptote, and to the left, as our x values approach it, our y values are dropping off to -infinity. And as we approach from the right, our y values are shooting up towards +infinity. So we definitely do not have them meeting anywhere near that line. So since the limit as x approaches 2 from the left is -infinity, and the limit as x approaches 2 from the right is +infinity, we have to conclude that the limit does not exist. Now in that example, we saw that our y value, the answer for the limit, can actually be positive or -infinity. Well, now we're going to look at what happens if we want x to approach positive or -infinity. And one major difference between finding limits as x approaches infinity and x approaches a regular number is that you're only going to have a one-sided limit. When x is approaching 3, you can look at what happens to the left and right of it. But if you're having x approach positive infinity, you can only look at it as it's going from the left. Or if you're going towards -infinity, you can only look at it going from the right. So these limits generally will be the same as the horizontal asymptote of the graph. So if you have a horizontal asymptote, that's pretty much going to be what you're going to see. For example, give this a try. You're going to find the limit as x approaches infinity. Pause the recording, give this a try, and resume to check your answer. All right, looking at the graph, as x gets larger and larger and larger, it's clear from the graph and the table that the y values are approaching a single number, and that number is 3. Now note that this is the horizontal asymptote for that function. If you think back to what we learned in algebra and college algebra, how you find horizontal asymptotes, 3 is the horizontal asymptote. So you may also notice that this is the same as the limit for the function as x approaches -infinity. Now that may not always be the case, but it is here. All right, so let's find the following limits for this particular function. Pause the recording, give it a try, and resume to check your answer. Okay, so as x approaches 1 from the left and the right, we see the y values separating greatly. From the left, it goes to infinity. From the right, -infinity. So this limit does not exist. As x approaches 2 from the left, and y approaches 5. And as x approaches 2 from the right, y approaches 5. So the limit does exist, and the limit as x approaches 2 of f of x is 5. And as y approaches infinity from the left, or as x approaches infinity from the left, y approaches 6. The limit exists, and the limit as x approaches infinity of f of x equals 6. So here's the summary of our section. If you want to pause and look over this, this is just kind of a wrap-up and a synopsis of what we just talked about. So pause for a minute, look over this, and then continue. Video is going to be additional practice, so if you will pause the recording to try the problems, Resume to check your answer and continue this way through the end of the recording.